Hello everyone. Today I would like to introduce our paper titled Enhancing Prompt Generation with Adaptive Refinement for Camouflage Object Detection. The author information is shown on the slide. When we rethink camouflage object detection, we notice two main challenges. First, the model often lacks task-specific clues, like the category, the size, or the location of the object. Second, there is usually strong background noise, which makes the object boundaries unclear and the feature learning quite weak. To address these issues, our approach makes use of vision language models to automatically generate multimodal information. On top of that, we introduce an adaptive refinement module, which helps to reduce the domain shifts and provides high-quality prompts for SAM. Our work makes three main contributions. First, we propose a cost-effective way to automatically generate mask prompts using Bleep. This gives them effective guidance without the need for extra training or fine-tuning. Second, we design an adaptive refinement module which refines the prompts and fine-tunes SAM image encoder. So the segmentation becomes more accurate and robust. And third, by introducing auxiliary embeddings from Bleep, we provide SAM with richer features for this task. Next, let me walk you through our method. First, Bleep takes the input image and automatically generates multimodal information. From this, it creates the initial prompts as well as an auxiliary embedding. Next, the initial prompts often suffer from locality issues, so ARM applies multiple adapters to extra visual features from both Bleep and SAM. It then uses attention to refine those prompts into more accurate masks, while at the same time fine-tuning SAM's image encoder. Finally, the SAM decoder brings everything together. It receives three kinds of inputs: the image embedding, the dense mask prompt embedding, and the auxiliary sparse embedding. With all those combined, SAM can effectively handle the camouflage object detection task. And as you can see here, we compare our method with other state-of-art models on 4 different datasets. Overall, our approach shows outstanding performance across multiple metrics. In particular, our methods perform especially well on the S measure and the maximal F measure, which means it's very effectively at localizing targets and capturing the structure of objects, even in complex scenarios.
Here you can see the upper figure, which shows a comparison between our method and other state-of-art models on two of the most challenging samples. It is clear that our approach achieves a much better overlap with the ground truth compared to the others. Even in the first difficult case, where there are several small camouflage objects, our method is able to detect and segment more of them accurately. In contrast, the other models tend to miss some of those tiny objects or produce incomplete results.
And we visualized both the initial prompts and the ARM refined prompts. The initial prompts usually only capture part of the target because of domain shifts. But after applying ARM, the refined prompts are able to cover the target regions much more completely. And well, that's all for our presentation. Thank you all for listening.